Hey guys, you were asked to complete your student notes, pages 13 and 14 and I believe 17, so we're going to take a very quick look at that. First, what is resistance? Not too difficult. Resistance is simply a measure of the opposition to the flow of current. So it's a specific number and there are a few properties that affect it. So here they are. The first factor that affects resistance is going to be the material itself. And materials have a property called resistivity. It's not the same thing as resistance, although they are related. It basically is going to tell us how difficult it is for current to travel through a material. There are a couple of other factors, though, in addition to resistivity. And the first of those is the length of the conductor. So what you will find is that resistance is directly proportional to the length of a conductor. And that is what this little bit of math here means. So the longer your conductor gets, the more resistance it will have. And the shorter your conductor is, the less resistance it'll have. Very straightforward. Okay, the third factor that affects resistance is cross-sectional area. So what we mean by that is if you apply a voltage to both ends of this conductor, so if you imagine that here you have positive potential difference and a negative potential difference over here, what we're looking at then is this cross-sectional area and how it affects resistance. And the same thing up here. Okay, so the effect here is pretty straightforward. Resistance will be inversely proportional to the cross-sectional area of a conductor. In other words, the larger this cross-sectional area is, the easier it is for current to flow through the conductor. You can think of a conductor as maybe a highway. So if you imagine one of Tokyo's very narrow streets, it is hard for cars to get through those narrow streets. But once you get onto a nice wide freeway, the cars can really open up. They travel much more easily on wide open freeways. So cross-sectional area is kind of like that. So it's inversely proportional. And mathematically, this is what that looks like. Okay, so here we have a couple of graphs, and this is called Ohm's law here. So mathematically, the relationship between resistance, voltage, and current is given here by resistance is equal to change in voltage divided by current. This is a very common way to show Ohm's law. I kind of prefer V equals IR just because it's easy to remember. Ver, right? But anyway, different strokes for different folks. This is kind of a more accurate way to represent Ohm's law, though, because resistance is dependent on both voltage and current. So there's a relationship of dependency, which means that this is kind of a more appropriate way to structure the equation. Okay, I'm not going to read these points to you, but I am going to point out that your graphs should look like this. If you have a linear relationship between current and voltage, then we have what is called an ohmic resistor. And what that means is that resistance will be constant. Okay, a non-ohmic resistor means that resistance is going to change as you increase the current through the resistor. And so most conductors are actually non-ohmic. It takes a pretty special conductor or a pretty special component to have an ohmic resistance. So, for example, a light bulb is an example of a non-ohmic resistor. So if you measure the current and voltage across a light bulb, what you'll find is that the relationship is not constant And that is because the filament of a light bulb heats up, and that generally increases the resistance of a substance because the atoms or molecules are vibrating really hard and they're obstructing the flow of electrons. Okay, questions 1, 2, and 3. I'm just going to show you the answers. Not too much here in the way of challenge. So if you need to pause the video to look at these, feel free to do that. Last thing I want to point out is that even though number 3 says to do it in 2 parts, you could do it in 1 part, just doing a little bit of substitution here, and you'll get voltage is equal to change in charge divided by time times resistance, or Q times R divided by time. See, isn't that nice? Handy. You may or may not want to remember this. I mean, I think it's pretty straightforward to work it out. The other thing I want to point out here is that this heater has a voltage of about 120 volts to 2 significant figures, and this is a very appropriate voltage for an appliance. So when you go to your wall plug, that wall plug in Japan will have a voltage of about 100 volts. Okay, so after I did the math here, I didn't really need to do anything else because I knew that 120 volts would be an appropriate value for an appliance in particularly the United States. Most appliances are running on 120 volts in the United States. Japan voltages are slightly lower, but most appliances will run fine on a Japanese voltage or a US voltage or vice versa. 240 volts would be a little bit more problematic. 240 volts is common in Europe, as you world travelers may perhaps know. Okay, guys, if we look at page 17, it is just a checklist of where you are right now. So hopefully you've filled this in, and that's going to be it. Okay, so gentlemen, have a great day. Thus ends this video.